So it is such a treat. It's actually been, I just looked, so I did WFD 3 years ago. I saw many of you. So it's very nice to have you back here at Levi's, and we're going to show you around and show you kind of behind the scenes a little bit later. But we've learned so much. I think all the vendors have learned a huge amount since 2012, 2011 timeframe when a lot of the first stadiums were being built. And so want to give you kind of the best understanding we have today of how to build these networks successfully. And it is really inspiring to see that Wi-Fi is actually incredibly stable and can actually support multiple gigabits per second load in these types of environments on a sustained basis. We're not going to talk too much about Levi's. There's videos online that deal with that. What I really want to talk to you about was how to design and dimension high density systems. So we're going to talk about dimensioning. Then we're going to start talking about channel plans. How do you do capacity planning? How do you estimate how much capacity, how much in bits per second that a network like this can actually produce, both at a system level and at a per device level? We're going to probably run through RF design super fast, and if I have to clip an area, probably we'll skip over this. Really want to talk about collision domains. This is an area that is not really been well documented or described, and it's really key to making these types of environments work. And when I say these types of environments, I don't just mean stadiums. I'm talking any kind of high density environment. And then we'll start and hopefully finish an actual real world example on large auditoriums. So we published a new validated reference design in March, and everything that I'm talking about is described in there and in much more detail, right, than we have time to go into here. These are free, they're downloadable from the web. How many of you have actually pulled the guide?
Oh, yeah.
Oh, fantastic. Okay.
That's when you just drop the mic and walk away.
Yeah. Okay. All right, we're done here.
Yeah, I guess I'm finished. So something we did, for those that haven't seen the guide out on the internet, we did something a little bit different because high density is such a big topic, and because these guides can get pretty long from all the vendors, so we actually broke it up into 5 different documents of varying sizes. So they range from I think 25 pages to the biggest one is the engineering guide. It's a little over 100 pages, but you can kind of mix and match the ones that are right for you based on your job function. So if you're an architect, you might want to read everything. If you're just if you're a salesperson putting a bill of materials together, maybe you just need to read the planning guide, that kind of thing. Okay, so as I said a minute ago, high-density networks are not just stadiums, it's everywhere. It's airports, convention centers, malls, you name it. So I was in Bangkok 2 weeks ago, and this is the check-in counter. Maybe you've been there. So there are 20 APs around each of these departure check-in stations, and every queue has its own access point. So there are 5 operators in Thailand, and every one of them offers public Wi-Fi service. So there are actually 5 different SSIDs on the air here, and there's over 300 access points in this departure area. Here's a mall in Thailand. So Thailand is like the most incredible for density. All of Asia is like this to one degree or another. And by the way, this is the future of the United States. It's the future of Europe. We're all heading this way, right? So here are the malls. So there are, again, 5 operators. In this photo, I've got 4 APs highlighted. They're within a meter of each other, right? And so there's 4 different vendors on that ceiling. The 5th operator is yet another vendor. And you walk 15 meters and you find another cluster. And you walk another 15 meters, you find another cluster of APs, right? So it's really remarkable. So obviously the CCI is priceless in this environment. So
are they using both 2.4 and 5?
Yeah. And of course, these are malls with multi-story open atriums, right? So Signal does a really good job of moving from level to level. So these design principles we're going to talk about are applicable in a really wide variety of circumstances, right? Want to walk you through basically the dimensioning process that we recommend for these systems. And the process that's laid out in the VRD basically has 9 steps. We start with the devices. and then we go to the WLAN infrastructure. And then one of the things we did with the new guide is we actually pushed it out to go beyond the WLAN infrastructure all the way to the service provider edge, because there's a lot of other components, right? You connect with your smartphone or whatever, but if the DHCP server is slow, right, or the WAN link is small or whatever, it looks to you like the Wi-Fi sucks, right? So when you come in to do the designs, and again, it doesn't matter if it's a hotel or a college or any, whatever, you really have to think of it from an end-to-end perspective. So these are the basic steps, and starting with step one, which is, okay, what are the KPIs? What are the key design criteria that you have to manage or choose as you're entering the dimensioning process? So the first is, what is the capacity of the area? How many people can it hold? That might be a seating capacity if it's a lecture hall, that type of thing. In the airport example, maybe it's just a crowd capacity. Maybe it's a standing capacity, right? Every physical space is engineered for a certain number of people. You see on the door, right, maximum occupancy 54. So there's a fire code aspect of it. So you find out how many people the device the environment is rated for. Then how many devices per person am I expecting each one to have? And we basically found, after doing some research, that we kind of could boil the world down into two buckets. Either you're doing what we call the work study use case, which means you're in this type of environment, you have a keyboard-enabled device, you're taking notes or something in addition to the other equipment devices that you might have with you, or you're what we call the fan/guest use case. So you're at the stadium, you're at the concert, that type of thing. And in that case, you might have more than one device. I might have my watch or what have you, but we're basically concerned about supporting one device, right? So you boil that down, and then you have to say, what is the percentage of those users that we expect to connect to the network at some point during the event? So that's the take rate. And that's going to give us the ADC. And we're going to walk through examples of this here in the next slide. I'll jump down to the second two items. So the average good put per user, this is really what the customer's expectation is. A lot of RFPs have will specify a certain number of megabits per user. We generally guide customers, depending on the type of the environment, 512 kilobits to 2 megabits. 512 feels pretty low. That would apply to a really, really large ultra-high density area. Basically, the bigger the environment, even after you have a really good radio design, you use special antennas, you've got optimizations on the controllers. If everybody hits that network at once, physics just says that there's only a certain amount of airtime that's available, right? So the bigger the facility, basically the lower that number needs to go, as opposed to a lecture hall with 500 seats, let's say, where you could get multiple megabits. And I'll walk you through an example of that. So you want to be a little smart about that as you work to the customers. And then from a band split perspective, how many users do you want to get on each band? And generally, we want to put more users on 5 gig for obvious reasons. So associated device capacity. So this is the key number in this step. And basically, we've walked through the KPIs. So now what we're going to do is say, okay, we just apply them. So you take the seating capacity, multiply it times the take rate, times the devices per person, and a couple simple examples, right? 70,000 seat stadium, 50% take rate, 1 device per person. So my ADC is 35,000, right? Pretty straightforward. If I have a 1,000 seat lecture hall, right, 2.5 devices per person, 100% take rate, I've got to support 2,500 users, right? And that's not just, so that's associations to APs, it's also network addresses, right? It's network resources and so on. We'll get into that here on the next slide. So the ADC is helpful a couple different ways because it literally does translate directly into address space, right? And if I'm breaking apart, I'm going to have different roles, right, that I'm supporting in the environment. So my guest role, oops, sorry, let's back up. So my guest role, I have, so many devices now. Remember that you're not designing for now, you're designing for whatever the end of the lifespan of the network is. So 3 years, 5 years, whatever it is in your particular environment. So I've got that number of devices, and then this is my band split. So to accommodate that, I need a /18, right? And then these other roles, you're going to come in on a .1x or a secure network. We're going to put you into the correct VLAN, and we'll size the subnets accordingly. And we're going to walk through a couple examples. Here's another version of this. This would be for a large university with a lot of lecture halls, and the idea here is that we're summing basically all the lecture halls together. We're going to put all those users in one VLAN. And then the faculty, of course, are another significant user community, so I need a /20 for the faculty. So how do I get from that to AP count? Basically, you take the 5 gigahertz number, the 5 gigahertz ADC, and you divide by a number of associations per AP, or sorry, per radio, and we generally recommend 150 as the target there. And that is about 60% of the capacity we support. So you can go all the way to 255 associations on an Aruba AP. But we want to leave headroom as users move in and around, and then clients ultimately are making the decision where they go, right? We can do a lot of things to impact that, but depending on what happens in the crowd, particularly here, everybody goes for the gates, right? You have these huge spikes that suddenly happen at the gates, and you'll see all the APs are suddenly 500 plus users on them, right? So from a capacity perspective, we want to have, we don't want to plan for that. We want to plan for a more even distribution. And the default out of the Aruba controller, we ship from the factory with 64 users per radio enabled. So in the config section, you need to crank that up to 250, 255. Real quickly on if we look past so I'm skipping the sections on how do you dimension a controller, how do you dimension some of the rest of the WLAN infrastructure, that's all in the VRD. If we jump out to the LAN, then you want to make sure, again, we're recommending large flat VLANs. They're very helpful for dealing with a lot of the mobility events that you have at a facility like this. Again, the clients are roaming. If you need multiple controllers because of the size of the facility or the scaling requirements for the facility, it's possible that you can be roaming between controllers. And so keeping it all L2 makes it very simple, keeps it very fast, and so on. But that means that you need to make sure that your core switches, right, are able to handle the load. So for example, here at Levi's, we're running a /16 on the FAN network. The core switches can easily support that, and we just work through all that in the diligence steps. Remember that your WAN uplink, and we're going to talk about how to estimate capacity. The controller uplinks are twice the WAN capacity because all the traffic hairpins through the controller on its way out. From a server perspective, fast DHCP servers are really critical, and you want very fast transaction times. It's really not the rate of transactions that's the key in this type of environment. It's the speed with which they are fulfilled. And you can use the DHCP arrival rate. We've done studies, and typically what you see, if you look at just the tickets being scanned at the gate here, on average, the peak is about 30 minutes before kickoff, and it's about 5% of seating capacity. So you can use that as just a very reliable metric to sort of size a bunch of different servers, Radius and ClearPass and so on.
How did you get to the 5% number? How did you get to the 5% number?
We actually looked at so one of the nice things about the Venue Next application is that they're actually charting, we have real-time information on arrival rates at the gates. And so we just break it down, and you can see where the peak is, right? And you just take the 5-minute interval around the peak. Right? It's surprisingly lower. It's a lot lower than you just would expect. Right? The stadium holds 70,000 people, and you would just think it would be a higher number. But if you break it down, it's a lot more manageable. On the WAN Edge, so we'll get into the estimation process here in a minute. But sort of the meta point of this slide is you really should be planning for a gigabit or more of backbone capacity. A well-designed high-density network, particularly if you're using DFS channels, and I'm going to make that argument in a second, should easily produce a gigabit per second if it's offered to the network. And of course, it's going to be HA. So channel plans and bandwidths. So you've heard this. Some of you have heard this from me before. This is a map of the FCC channels, and of course, it varies from country to country. The triangles are the 20 meg channels, then we have the 40 megahertz channels and the 80 megahertz channels. And you'll notice that let's see, the AirPlay is moving a little slow here. So I have fewer channels if I use channel bonding than if I keep the channels small. And we recommend that you use only 20 megahertz channels in the high density environments for a bunch of reasons which I'm about to get into. But you can see just sort of visually here that I have a lot more to work with if I choose not to bond those channels. And there's this section in here. We lost a few channels a couple years ago due to some issues with the FCC that they've taken away. Those channels are coming back in some of the new products. The FCC has finally decided how they wanted to handle it. So we're starting to certify new equipment. But so it's important to check as you're, depending on the AP model you're choosing, what is the available channel set for it. We recommend that people do not use channel 144 yet because they're only visible by AC devices, and AC devices are about 20-25% of the market right now. So none of the 11N devices can see them. So I think it's going to be another year or so. So many of you have heard this from me before. Use DFS channels. This may vary depending on the vendor that you're working with, but I can tell you from an Aruba perspective, we have equipment that's extremely reliable in DFS environments, and because of the capacity that is represented by those channels, we simply cannot leave them aside. We need to take advantage of them, particularly in an environment like this. So why? One of the reasons is that the number of channels, of course, is a big limit on capacity. You may have also seen one of my other talks online about what happens as you add more and more stations to a Wi-Fi channel. It gets the capacity of the channel actually decreases the more stations are contending. So I can increase the capacity for everyone by distributing a given number of stations across more and more channels, right? So these are some of the key reasons, and high-density networks ultimately are about trade-offs, meaning that the design criteria that I use when I go into an enterprise environment or a hospital or maybe a warehouse are different than they are in this type of environment. In the hospital, every device has to be connected all the time. The SLAs are extremely rigorous, right? And I would not accept a medical device that was falling off the network periodically. Right? We just wouldn't, right? We also want to deliver the fastest possible experience, the highest burst rate, right? Because in the enterprise environment, there's a lot of file transfers, things go to the printers and so on. So we want those to be very, very fast for each and every user, right? So that's one set of design criteria. In this environment, the expectations are different. Instead of designing to maximize each and every user experience, I am designing to a sort of lowest common denominator in the sense that I'm delivering a minimum amount of performance, a megabit per second or whatever it is, to a very large number of users. So I have to make trade-offs in that environment. And so in that context, now we start to get into clients that may or may not support DFS and the issue of the radar false positives.
Mm-hmm. Yeah. Do you have any insight into how ARM will stack channels? In particular, will it stack DFS channels next to each other, or will it sprinkle in non-DFS channels? I mean, does it take into account when it's doing its channel planning DFS next to a non-DFS channel to mitigate those?
I don't believe that we do that today. That's something that we might be delivering down the line.
Okay.
And it's not just DFS. There's a lot of other intelligence, right? Particularly as we're into wider channels and some of the other complexity that comes with AC and so on. That there's a lot of room for improvement in the radio management algorithms, I think, from all the vendors. Yeah.
Sure. Okay.
Just real quickly on the client capabilities. So there's basically two issues with DFS. One is, can the client support them, right? Can the client see the channels? And most of the time now, the answer to that is yes, with the exception of the Google Nexus devices, which I understand the new crop does do DFS channels, but that was kind of the last batch of, or the last vendor that hadn't yet enabled those channels. So the the Google devices have now caught up, and we still have some older Android devices that are in the market that may or may not be able to see the channels. But again, if you think about the high-density environment, the requirements are different, and we're going to have a lot of overlapping coverage. So it's not the case that I won't be able to connect if I have one of those devices. It's just that I might connect to an AP that's 2 or 3 APs away. So my signal might be a little lower than it otherwise would be. So we ultimately will take care of those clients. And then the second issue is the radar events. And this comes down to basically how stable is your equipment from a false positive perspective. And this is something that's really important that customers test if they're going to roll out a high density network. This is a key criteria that should be part of the evaluation process. And vendors should have to come in, we should have to come in, everybody should have to come in and demo their equipment. And this does vary from vendor to vendor, particularly under load. So what I would tell you is if you do a lot of data transfer on an AP or a series of APs, you can flush out how solid a particular AP model might be in this regard. And since you all happen to be here, I wanted to just very quickly, Sean, if I can just grab the chair for a second. I can't normally do this demo, but
Who do we log in?
since you're here, so I tell people always ask me, is that real, right? So let me show you. So we have 4 controllers in the stadium, and I've logged in already. You can see this is real time, and so the controllers have been up. We did a maintenance window 34 days ago, so we rebooted all the controllers. And if I say show log all, include radar, so this controller has all of the lower bowl APs on it, and there's nothing in the log. If I go to this one, we will see some events. So there are 5 events in the last 34 days on this controller. If I say show AP, there are 339 APs on this controller in 34 days. If you do the multiplication, it's over 38,000 AP days, right, worth of exposure on these channels. And you can tell that these are not actually real radar events because they're not periodic, right? If it was radar, they would keep cycling. And one AP is repeated twice, but it's also different APs. So the other thing, if it was real radar, they should all go, or a significant chunk of them should go at the same time that are on that channel. And we can look at the other controllers. Right, nothing, and then I think this one.
Well, how true is what you just said, though, Chuck? Or there's a nuance to that, because if they're not all in the same area, there's thresholds and all of that, right? You said they should all go, or a bunch of them should go, but
Radar's not going to hit just one AP, right?
No, it'll affect all.
We're required. So there are on average there are 60 APs on every channel in this facility, right? So you'd expect a significant chunk of those, if not all of them, that could detect the pulse. They would all have to transit at the exact same time, right? So there should be, if it was real radar, we would see, and we do see this in like Lower Manhattan or certain other marine environments. The signature, what you see in the logs when there actually is real radar, is very, very different than this. So this would tend to be a signature that these were just false detects for whatever reason at that particular time.
Yeah, I didn't ask my question right, but I'll get you afterwards if there's time.
Okay. So hopefully that's convincing. This is basically a huge DFS probe, if you want to think of it that way, right? We're 4.5 miles from Moffett. We're 3.5 miles from San Jose, right? We have line of sight to SFO and Oakland up on the north end of the bay, right? They're 25 miles away. I just want to show you that in an environment, again, not every environment is radar free, but even if you, we don't have a lot of time to get into this, but if you do a radar survey prior to deploying the network, which would be a best practice, that would be a service that should be provided as part of the deployment process. If you go through that survey and you find radar, chances are it's only a couple of channels that are impacted. So the rest of the channels would be available.
And you would manually exclude those or let DFS take them out?
You would manually remove them from the plan. Okay, so back to this guy. So just to kind of then finish out the channel width discussion. So we talked about the number of channels, basically maximizing that by using DFS. So why use the narrow channels? So there are a number of reasons. The first reason is that you want to increase the distance between the APs that are on the same channel. And we're showing, a 3-channel plan like you'd have in 2.4, a 9-channel like you'd have in 5 gigahertz, and a 23-channel like you'd have if you were using DFS. And you can see how the distance between the same channels increases, which helps me with adjacent channel interference. And in an environment like this, if I'm attempting spatial reuse, I increase my probability of success if I have more physical separation between those APs. The next reason is that I'm reducing my retries. If I'm bonding channels, then I take the risk that one of the channels might be clear. If my primary is clear, but my secondary is busy, the whole transmission might block, right? So using the smaller channels allows them to all go at the same time. Higher SINRs. When I use wider channels, one of the principles of radio is that for every doubling of bandwidth, my noise floor increases by 3 dB. At 80 megahertz channels, my noise floor is actually 6 dB higher. But my transmit power from the APs has not changed. And so the net effect is that my SINR at the client is basically being compressed, which is going to reduce my data rates, and that's going to slow the whole network down. And then the last reason, and some of you may have seen this from me before, but we've actually tested this, and we've just very quickly, so we tested 100 stations with a single 80 megahertz AP. We took that group, broke it into 2 groups of 50, and tested it with a 40 megahertz AP, and then we broke it again into 4 groups of 25 with 20 megahertz APs. And each of these tests uses the same amount of spectrum. It's channel 100 through 112, same number of stations. These last 2 tests are actually, we have adjacent channel interference to worry about, right, as opposed to the first one. So these are actually harder tests. And what we actually found in the lab is that VHD 80 starts to fall off around 25 stations, and VHD 40 falls off around 75 stations. And this has to do with primarily what's going on at the MAC layer under large amounts of load from stations. There's other stuff from me online on the internet about how this works, and the theory guide from the VRD explains this result in detail. But the net is the 20 meg channels, for all the reasons that I've just been through, are really the right choice. So how do you estimate the amount of capacity that you're going to have in a high density network? The way that we've learned through doing this for a while is we really want to focus on this concept of channels. So we're going to start with looking at how many channels we have available, and then we're going to work separately backwards to what a device has available. So if you, we talk about an idea in the book called total system throughput, and basically that's the sum of what the channels are capable of delivering. So if you imagine that each of these boxes is basically 50 megabits per second worth of capacity. So in 2.4, I've got 50 plus 50 plus 50, so 150 megabits of capacity. In 5 gigahertz, I've got more channels, obviously, so that's going to vary from country to country, but or whether you're using DFS or not. But let's say I've got 50 plus 50 plus, if I have 20 channels, then I've got 20 times 50, that's a gigabit per second. So I take the gigabit plus the 150, so that's 1.15 gigabits per second. That's my total system throughput. That's what the network should be capable of delivering. And that is the size of the pipe that I need at the WAN edge, right, as well. And you'll notice we haven't talked about devices yet. We've just talked about what the channel is capable of supporting. So I can go the other way, and I can divide up, right, based on the number of devices that are trying to compete for the channel at any moment in time. If I've got 50 devices, and you'll notice that there are APs in the boxes as well as clients, because if they can hear each other, they're competing for the same channel, they're competing for the same airtime. Then if I've got 50 clients competing for that 50 megabits, then on average, each device is going to get a megabit per second, right? So that's kind of how that works. And so just from a mathematics perspective, the total system throughput is the channel count times some throughput value per channel, and we'll explain how to pick that, times a reuse factor. And generally speaking, the reuse factor is going to be 1. And just quickly, I'll move through the channel count. So how do you decide how many channels? We kind of set that up already. So you start with your channel plan in your country, your regulatory domain, decide whether you're using DFS or not. So that's going to give you a total pool. But then you may deduct channels from the pool. You're going to take out 144. If you're holding back a house channel, like here we actually hold back channel 100 for concerts and so on. So we just have that, it's not in the plan. And we deploy that as needed for events. If I found radar channels during my survey, right, I would take those out. So I end up with a net channel count at the end. So that feeds my methodology. So the next step is I want to choose a throughput value. So in the example a minute ago, I talked about 50 megabits per second. Well, where did I get that from? That was kind of a hypothetical example. We actually tested this, and so just jump to the next slide real fast. So this chart is based on a lab I have in Sunnyvale. So these are real over-the-air numbers, and quite a few of you guys have seen this chart already, but basically the purple line on the bottom, these are smartphones from 10 to 100. The orange line are 2-stream laptops from 10 to 100, and the red line is 3-stream laptops. And then the dashed lines are various combinations of the above, because we never have a pure environment, right? Depending on, in that fan/guest example, I'm going to have a mix of 1-stream phones and 2-stream phones, that type of thing. And that's going to, so we found that the spatial stream mix in the environment has a real profound effect on how much capacity I can expect out of it, because they support higher rates. So the way you basically pick the number is, I have to pick a coordinate here. So I go out on the x-axis based on my environment. If I'm in a lecture hall type of environment, I'm going to choose a lower value. If I'm here in the stadium, I'm going to probably go all the way to the right. And then I have to choose a y coordinate, and that's going to be based on the spatial stream mix in the environment. So out here at the stadium, I'm going to choose something, more like in the 40 range, whereas in a lecture hall, if I'm expecting, a 30-60-10 type mix, I might be in the 70 to 80 megabit per second range. So that's how I pick those numbers. These are lab quality data. Again, there's no interference in this environment. There's no, we have exclusive use of the spectrum. So the next step is I have to add an impairment. I have to reduce that number by some factor, and that's going to vary based on the type of environment that I'm in. And in the guide, we provide sort of guidelines that you should apply. And this is kind of where your judgment as architects, your experience as architects comes in. And also, from a services perspective, again, you want to bring in the spectrum analyzers. You want to qualify the environment. If it's a particularly clean environment, you might use a lower number. If it's a dirtier than normal environment, you might use a higher value than this. But just as kind of a starting point, this is the methodology. And then spatial reuse. So generally speaking, you're going to use 1 for this value. I tell people, people laugh, but I basically, my usual line here is that if it's 1 unless you can prove that it's not 1, right? And it's very, very difficult to achieve this. This is basically, how do I get it higher than 1? Well, that means that 2 devices on the same channel can transmit at exactly the same moment in time. And that's extraordinarily difficult to achieve. But that doesn't mean that I'm not reusing the same channel number, right? Anytime I've got more APs than channels, of course I have to reuse the same channel more than once, right? So I said earlier here, right, there's 1,200 APs. I have 20 channels. So on average, there's over 60 APs on every channel in this building, right? And if we go into the bowl, over 1,000 of those APs can hear each other, right? So this is really the critical distinction that that we have to kind of be clear on. So in order to sort of demonstrate this, again, we looked at the controllers earlier. I was at a stadium recently, and just to kind of drive the point home, because people think that people don't understand how far radio works, right? You all work with this every day, and you've got a good sort of intuitive feel for it. But we connected to. So this, if you look at this little black speck over here in the distance, so we did 2 tests. This is my colleague Ben, who's on the far side of the stadium. So he's 160 meters away from me. And there's an AP underneath the seat, and there's an iPerf server behind the access point. And we connect to it with, we started with a 2-stream AC device. And you can see the iPerf results between 40 and 60 megabits per second at 160 meters. Okay. And then we connected with the Galaxy S4, so a 1-stream AC device. And we're pushing, you know, a high of almost 30, a low of in the 7 range megabits per second at 160 meters, right? So you could say, well, that's an access point, right? That's an enterprise AP. It's got a powerful radio, you know, and so on. But the smartphones have really poor radios in them, right? So they're not that powerful. Well, we tried that test as well. So it's easy to do this. So we set up. So Ben turned on his iPhone and put it in hotspot mode, right? And I connected to his iPhone over 160 meters. And then we just ran a speed test. And we pumped 11 meg down. And I guess 10 was the final number. And 7.4 meg up. And then we got out the 2-stream tablet. And we're going to do a little better because the second chain is going to improve, right, for the usual reason. So about 10 meg, 11 meg down, and 11 meg up. So that's smartphone to smartphone and smartphone to tablet. So this is, when we talk about reuse being very hard to achieve, this is what we're dealing with, right? The radios actually are tremendously powerful. The MIMO radios are very good at recovering signals at very low levels. And so, you know, again, there's no crowd. There's some other things that during a real event are going to reduce those numbers, right, and make it lower. But just from a baseline design perspective, this is the challenge we have to manage, right, as design professionals. So just to pull it all together, so let's do a couple of examples. So here are just the 3 tables. This is the same information we've just walked through, just in kind of a condensed form. And so let's look at a lecture hall scenario with 9 channels. And again, because it's a lecture hall, I'm going to have fewer devices present. I'm going to go with more of a 50 concurrent user target. So I'll choose 100 megabit as my unimpaired value. And then my impairments for the lecture hall are 5 and 10% respectively. And so if I use 1 reuse, then my total throughput is, it's just multiplication. So it works out to 1.1 gig. In an arena environment with 20 channels, so if I'm using DFS now, I'm going to use I'm going to go over here to the 100 concurrent number. So I'll pick 40 as sort of an average of the 2. And then my impairments are a lot higher, so 25 and 50% respectively. And with 1 reuse, I end up estimating that I can do 660 megabits per second total offered load in that, total absorbed load in that environment, right? And then if we look at a spatial reuse example, so let's say now these are the same numbers, except now I've got a design that needs 4 reuses. So now the numbers quadruple, right? If I get reuse, it applies to both bands, right? So I'm multiplying both the 2.4 and the 5 gig numbers. And so I end up at 2.6. But if I make this bet and I'm wrong, if the design doesn't perform, right, then I'm obviously not going to hit that kind of number. So this is the TST concept. And again, you can see how this directly goes to the WAN edge. It goes to how big the links have to be off the controllers and so on. But we have not yet answered the question of what the devices get, right? So let's go there next. So the way I do the device calculation is I take the TST, so we start with that, and then we basically divide into it by the number of devices that we're expecting to hit the network at the same time. So it's the instantaneous device count, basically. And that really simply is the total number of devices that are there times the duty cycle, right? So if I have 1,000 devices and a 10% duty cycle, then I've got 100 that would be hitting the network. We've already talked about ADC, so we'll skip over that. A couple of just suggested duty cycles. Again, this is your experience, right, and your assessment of the facility should govern what values you actually choose for each customer. It's going to vary depending if somebody's just doing social and email. It's going to be very low, right? If they're doing testing applications, it might be considerably higher. And then you basically we're going to go to the same sort of math.
Sticky clients, since you're doing that test at 160 meters.
Yes.
I mean, obviously clients I think would pick an AP when they get here, and then by the time they get to where they're sitting, they're probably still able to see and talk to that AP.
Yes.
Well, but that's with no bodies in the arena. I mean, that was 100% clear line of sight.
I'm just saying, I mean, even with bodies and
You stack a half a dozen bodies in between, in a row, in between that AP. That client had to have been at MTS 0,
even if you're
right?
picking an AP, just not at the front door, but maybe somewhere close to where you're sitting, but you end up, that client's still going to see that. It's still going to take that travel time.
Right.
I don't know if you guys can do anything about that.
So what we found, the way we used to do like band steering and some of those things is we used to do it on association. So when you basically every time you roamed, we were trying to either force you to 5 gigahertz or make some sort of decision, right, deny you access to certain APs. We found that caused a lot more problems than it solved. We had people flapping and so on. It's not so bad in a university or an enterprise type environment, but in this type of environment where you have a lot of candidates that the device can choose from, you can get a lot of undesirable consequences. So the way client match works is we actually wait. We don't try to move you at association. We let you kind of settle, and there's kind of a hold down timer for every client when it associates to the infrastructure that's a few minutes long. So we will wait to kind of see how you settle out, and then we'll decide, okay, are you in the right place or not, and then we'll try to move you to the optimal access point.
Thank you.
Was there another? Okay. So just to then finish out the example, so we'll take those 3 scenarios. So the lecture hall. So now we're talking devices, right? So now I would tell you that there were 500 seats in the lecture hall. We're going to plan on 75% take rate. So that's about 940 devices. And let's say that I'm going to put half of those on each band, right? So I got to get about 470 devices on each band. Well, now I can then pretty easily compute my per device numbers. I just take the same, so these are the TSTs that we calculated in the last go. And then I take my 479 times my duty cycle, and I get these megabits per device. And these are pretty large because it's a comparatively small facility. In the arena example, so if we move on here, so now I'd tell you that it's 20,000 seats, I think is the example.
It's doing the same thing.
Very slow.
It's doing the same thing, Chuck.
Is it?
It's showing it here, but not up there.
Okay. So.
Probably lost its connection again.
Okay. Well, anyway, so you have 20,000 seats, right? You can kind of see the math, right? If I take a 50% take rate, then I've got to get 10,000 devices on the network. And if I do a 75-25 band split, which is what we recommend in this type of facility, that means I've got to get 7,500 devices on the network. And if you do the math, you end up at about a megabit per second on 5 gigahertz, but you only end up at about 250 megabits, kilobits, or 300 kilobits on the 2.4 band. And then if you do the reuse example with the stadium, you can still hit approximately those same numbers, the megabit per second on 5 gigahertz. But again, as we said earlier, that design depends on me achieving the spatial reuse. And if for some reason I'm not able to do that, then my per device number is going to be a lot lower. So that's the capacity planning process that we recommend. So that plus the dimensioning process are kind of the two key planning techniques that you really need as you're working with customers around these types of areas.
Can I ask a quick question?
Yeah.
I'm working on a project right now, and it's an arena, it's a soccer arena, and I'm being shuttled through the large public venue team, specifically. And it's interesting to work with it. And I don't know if you guys have had experience with this, but basically,
Yep.
I don't get the blessing from Aruba unless it goes through the large public venue team to work on that. What are the requirements to be on that team? What is it that you guys are doing to make a different group special? Is it a certification completion? Is it prior installation? I mean, can you talk a little bit about that, because it's a new concept for me, and I understand why they're doing it, but I'm a little frustrated with it. So I'm trying to understand what it is that they're focusing on.
Frustrated on response time?
Response time.
Oh, okay. Yeah, because there aren't nearly enough of us that are doing this work, and there's a lot of demand, which I think is probably what you're experiencing. So yeah, I mean, generally speaking, it's people that have done these types of deployments before, and maybe not even stadiums, could be large convention centers or that type of a facility. And have kind of got the sort of hands-on experience to go with the methodology. So that's usually it. I'm surprised to hear that we're not responding as quickly as you need, but it's a very, as we all know, like there's more and more high-density networks, and so that group may just be backed up.
Okay. I'm just curious. I didn't know what the status of it was. It seems like a good concept. I just want to make, I don't want it to cost me business, to be honest.
Yeah, no, I understand. So let's take that offline, because we should, particularly if you've got something time critical, we usually, that's usually one of the key, prioritizing criteria, right? Is
me and everyone else.
When is
We're all top priority.
Yeah, exactly.